Okay, so in one of my last videos, we had a traveling salesperson problem that looked like this, where you have a traveling salesperson, maybe they're headquartered right here in city A, and they have to visit city B, C, and D, then come back to where they started, and they wanted to know the best route. The only way you can actually, for certain, figure out the best route when you have a problem like this is to do or use what's called the brute force algorithm, which we talked about in another video. That's where you just write all possible ways that they could travel between the cities, figure out the weights of that tour. So we'll call these numbers weights. They could stand for mileage, how much money it costs, how many gallons of gas it takes. We're not going to label them, we'll just call them the weight. So in this problem, we wrote out all the different ways they could travel from one city to the next and come back to where they were, added up the weights, and we found out that the best route was A to B, B to D, D to C, C to A, which had a weight of 145. Okay, well, if you have another city, like if there were 5 cities instead of 4, there's going to be n minus 1 factorial different routes, where n is the number of cities. So there would be 4 factorial routes. So 4 factorial is 24. You'd have to write out 24 different routes and add up all the weights and calculate which route was the best route. In this particular problem, with 4 cities, we only had to do 3 factorial routes, which is 6. So we did, in a previous video, we did write out all 6 routes, calculate the weight, and found out that this is the best route. A to B, B to D, D to C, C to A. And its weight was 145. Well, we don't want to do this if the complete graph is like K5 or above. We could probably do it for K5. Writing out 24 different routes isn't the hardest thing in the world to do. But for K6, you'd have to write out 5 factorial routes, which is 120. It gets really big really quickly. So remember that I called the brute force algorithm an inefficient algorithm. That's because even though it's the only way to actually know the best, specifically the best route for n of a certain number or higher, even 6 or higher, it would be very inefficient to do it by hand using the brute force algorithm. For K10, you'd have to figure out 9 factorial routes. 9 factorial is, let's see, what is 9 factorial? I'm going to try to do this without a calculator. You don't really need to see what I'm doing. Hopefully you can see the green marker, but I'm going to try to do this without a calculator. So I know that 5 factorial is 120. Then we have 42. Okay, I'm probably not going to be able to do this in my head. 72 times 42 times 120. You can already tell that that's going to be a really big number. One thing I can do is estimate it, right? I could say that's like 70, that's like 40, this is like 100. So this would be 2,800, and add 2 zeros to it. 280,000. I think it's actually, obviously it's a bigger number because I lowered each of these numbers. I think it's like over 300,000. So you don't want to have to write down 300,000 different routes. And that's just for K10. So it'd be very inefficient. Matter of fact, without a calculator, if you wanted to figure out the best route for K10 and you did it by hand, and you're like, well, the only way to actually figure out the best route is to use the brute force algorithm, it would probably take you, trying to be realistic here, 300,000 things. Let's see, how long would that take you? It might take you a whole year if you work like a 40-hour work week. So that would be the only thing you did for a year during the week, maybe. Try to figure that out. So that's why it's an inefficient algorithm. Well, luckily we have other algorithms that we can use that give you good routes. They might even give you the best route. You won't really know though, because if you're doing K10 and you use one of these other algorithms and you get a certain route that has a certain weight, you won't know if that's the best route, because the only way to know if it's the best route is to actually use the brute force algorithm. This is going to give you a good route. So let's do it on something that we already know. We're going to use what's called the nearest neighbor algorithm. We're going to figure this problem out using the nearest neighbor algorithm. Here we already do know what the best route is. When you have K4, it's not that hard to use the brute force algorithm, but we can practice the nearest neighbor algorithm on K4, and I'm going to make a K5 problem right after I do this. I'm going to just make one up. So, nearest neighbor algorithm. I'm not going to write down the steps. You can read the steps in the book, on the PowerPoint, in the other videos. They might, the videos that Pearson has, they might actually write down the steps. I'm going to talk about the steps, but I'm going to talk about them while I do an example. So, when you do a nearest neighbor, when you use the nearest neighbor algorithm to do a problem like this, they're going to tell you, or you're going to decide, or I'm going to tell you, which vertex you start at. So let's use the nearest neighbor algorithm. I'm going to abbreviate it, NNA, starting at A, because that's where we are. This is where our headquarters are for our business, that we're a traveling salesperson working. We work for this business as a traveling salesperson, and our headquarters is right here. So what you do is you look at the graph. Remember, this is a graph. It's called a complete graph. You're here. You have three edges leading away from you, going to the other vertices. What you're going to do is pick the edge that has the least weight to travel on. So you could go from A to B, which is 25, A to C, which is 35, or A to D, which is 50. Well, since A to B has the least weight, that's what you're going to do. So we're starting at A, and we're going to B. Once you're at B, remember, you can only visit each vertex once. We have to eventually come back to A, but now that we're at B, there's only two places we could go, C or D. B to C has a weight of 60, B to D has a weight of 40. So we want the closest, nearest, the smallest number. So we're going to go to D. Okay, now in problems like this where you only have K4, you have no choice of where to go next. There's only one other vertex that you haven't been to, and that's C. And then your last step is to go back to A. So if you notice, it's the same exact route as the route that we found had the the least weight. So in this particular example, this algorithm actually gives you the best route. And you only had to, you didn't have to write down all 6 and figure out the weight of each. Just use what's called the nearest neighbor algorithm. Okay, I'm going to right now make up another problem and do that. Okay, I don't know if I want to start to end this video here. I think I do. I think I'll do another video for the next example.